All right, I believe I'm live and we can start. So today we're going to talk about C++ STL performance. I'm Danila, work at Google. You can always reach out to me like by email, Telegram, or Twitter, like Danlark1, respectively. So a little bit about myself. I worked at Yandex on like core search engines for like a couple of years. Now I'm working at Google on distributed data processing. My primary expertise is C++. All these things that I mentioned above are like written in C++. It needs lots of low-level optimizations, algorithmic optimization, distributed systems design, etc. So I kind of know a little bit, maybe not a little bit, maybe like more about C++ STL performance than needed. So today's agenda, we're going to talk a little bit, actually, is C++ about performance. Then we're going to touch performance problems with C++ standard, like ABI problems, compiler problems, maybe some algorithmic problems. Then we will talk also not about problems. We will talk about like good stuff. And then in the end, we'll cover my experience from standard template library. What's actually used, what's forbidden, for which reasons, why, what were the practical solutions to several things. So let's start with C++ performance. When people are asking about whether C++ is performant, actually it is because of its philosophy. If you have been like in the C++ community for quite some time, you should know these two statements like from that were designed with C++. What you don't use, you don't pay for, and what you do use, you couldn't handcode any better. These are the things that C++ tries to stick to. Unfortunately, sometimes it's not the case for various reasons, and we're gonna cover some of them in this talk. Actually, there is like another side of C++ performance. I highly recommend you watching the talk from Chandler Carruth, that there are no zero-cost abstractions. So that's why it like reflects that even like standard unique pointer has some like performance cost. And this is just a great talk to watch if you want to know like about if someone talks about zero-cost abstractions, you can argue always there are no zero-cost abstractions. That's quite true. So what is STL? STL is standard template library. Everybody who like wrote at least several programs in C++ should know that. C++ provides some standard things. So why does it exist? It exists because it should provide like some standard things, as I could say, and like which are very convenient to use. And for example, the other thing, of course, is that if you want to, it provides some complex types that are very hard to implement by yourself. For example, standard things like standard vector. Of course, standard vector is not easy to implement. Like if you are not an experienced C++ developer, still standard vector has pretty good guarantees, like pretty understandable ones. And shared pointer, it's like it's on the one hand very useful thing. On the other hand, not all people can implement it correctly. If you go into details how shared pointer is done, there are lots of different, lots of complexity actually behind it. So C++, like in summary, standard library provides standard things and sometimes hard to correctly implement things. Then people like are using them on day-to-day basis, and like is standard library actually performant? I could say yes, but sometimes no. Maybe know appears more and more often with the development of new algorithms, new approaches, new hardware features, etc. People actually do care about performance. For example, in this on this slide, I presented like only several things that like appeared to my mind when I was like preparing for this. People are complaining about standard string. People are complaining about quadratic sorts. People are complaining about regex performance. People are like writing blogs that they like, I don't know, uniform in distribution was sped up by 2 times. So all this kind of stuff. People really do care about how standard library what standard library provides in terms of performance. Unfortunately, all these things with all these things with performance result sometimes one of the motivation to self-made libraries. For example, like several examples that came to my mind is like onSea library from Google, Foley library from Facebook, EASTL from EA, basically. So why do they do that? As already mentioned, because it's like standard for now, like appears like once in 3 years. It's not sometimes convenient to wait for it. Also, these libraries don't provide ABI compatibility, which we'll talk about later on, the API compatibility. So they can change over time, like more flexible. Of course, one of the main reasons, like whoever like, speed is simply money. If you spend a lot of CPU cycles in some function and you have a faster version of it, you just move to like faster version. So you'll not spend a lot of money on this. So now let's dive into the types and containers a bit. So we have some, like, it's my opinion, I can support with arguments, but outstanding types that came to my mind are like standard array, standard optional, standard variant, atomic, some types that provide views on the ranges, most of the algorithms. So why do I think they are outstanding? Some like deep reasons, like will come in several slides, but they are pretty simple, maybe except atomic, but atomic is a different thing. And they are pretty simple. They have pretty strong guarantees. They definitely provide the things, like you cannot do like much better. So maybe you can do like 1-2% better than these types, but for example, I haven't seen this, and also a lot of style guides encourage using these things, and for a reason. Yes, there are some types and containers that people are like debate about. For example, standard vector. There are lots of implementations of standard vector, like for example in GitHub, in open source. People like say, hey, my vector is 3 times faster than standard vector in like libc++, or like like for example, Facebook provided like a very good standard string that has like 1 byte for more for small string optimization than like libc++. Some standard maps, standard sets, they are just using some trees, and trees can be different, as we know from computer science algorithm course, and people still debate about that. Of course, yet, however, like readability costs sometimes outweigh the last percentages of what can be optimized in this, and also like some of the style guides suggest using these types from standard libraries. Some style guides suggest using their own types. It's different. Unfortunately, if someone decides to use another, and they pay the cost of education and readability in the future. And of course, there are some bad types. We will talk in more detail later about them. For example, unfortunately, standard pair is not what people think, or even standard tuple. Unordered containers were in the past years were highly criticized by their performance, and in the modern world, you can outperform these containers by a factor of 10 or 20. Standard regex also is a thing that's not used actually, I believe, almost anywhere. So it's like used for like some trivial examples, I believe. From my experience, that last two of these lists are banned in many places, and for a good reason. So now let's talk about something cool. Standard array. Why is that so cool? Actually, standard array is as I might say, is a piece of art. It has no constructors, no copy operators, no assignment operators. It doesn't have destructor. I don't know why I wrote destructors. It's a typo. Like destructor can be only one of the class. So it basically sticks to the rule of zero, and this is like one of the first thing I would like to say. Rule of zero really results in so-called triviality of types. So if you don't have something complex, if your type is trivial, for example, it contains some integers, some pointers, and if you copy it, and if you don't provide any copy operators, any destructors, any constructors, then your type is going to be highly optimized. For example, in this example, for example, in the slide, you can see if you copy one vector of standard array to another vector of standard array, compiler will likely generate something called memmove function. Memmove function is highly optimized for the platform. Likely you cannot do better in general case. So triviality is a very important part in the optimizations, and this leads us to trick number one. So try to make your type trivial. So that means that on the one hand, of course, there are lots of non-trivial types, but if you have some really low-level stuff, try to make it trivial, like in C. So what it means, actually, trivially destructible types, like in some architectures, they allow you to reuse the object. So what it means, if you stored in some register some trivial type, you can reassign this, reuse this register for other types, or I don't know, move this register around. So trivially copyable types is also one thing for the compilers to optimize. For example, if your type is trivially copyable by C++ standards, you can as we've seen in the example before, your type can be moved, or your type can be mem-copied or mem-moved. So these functions are highly platform optimized. So once again, you cannot do, I believe, any better than these functions. So trivially destructible types are really important, because if sys5 ABI says that if a C++ object has either non-trivial copy constructor or non-trivial destructor, it is passed by invisible reference. What it means, basically, if you have two classes and you marked one class, destructor one class as default, and the other one is like a zero, like empty body, so you'll have that in the first case, when you copy one class when you copy one object to another, you'll just move a register. In the other case, you'll move from pointer to a register, from register to a pointer. So this don't define the destructor unless you really need it. So write is equal to default, or don't simply write anything. For example, standard optional is a good example of this. So standard optional is has a trivial destructor. That's why it is passed basically in registers. And if you want to know, standard optional, basically a pair of the type and bool, if simplified, then you can just move the registers around and see see that operations with passing by value are pretty cheap. And let's talk a bit about optional. Like in optional, you have like how to like have a like what's like stated in the optional. In the destructor of optional stated if the type is trivially destructible. So if it is not trivially destructible, then it should call the destructor of the type. But if it is trivially destructible, then the destructor should do nothing. Basically, it's trivial. So even in the standard, we have the parts with triviality and which allow us to use some sort of optimizations. And if you think a little bit about how to implement this, you will not get to the right point, like I believe, easily. For example, your type might not be default constructible. How does standard optional T, for example, works when you just define it? So it is some sort of a hidden value somewhere. So, and you need to call the destructor explicitly if it contains a value. So this must be a branch in the destructor. On the other hand, if your type is trivially destructible, you should not do anything. And how to combine all these things? Unfortunately, this comes with a very complex structure of the optional implementation. So assume you have like class optional, and in libc++, what it does, it has like multiple inheritance. So basically, it has six classes that inherit one from another in a chain. So if you have a move assign base, copy assign base, move base, copy base, storage base, destruct base, and all these classes just have partial specializations. If something is trivially copyable, then you should, define it as default. If it is not trivially copyable, then the partial specialization should like explicitly copy the object if it presents in the optional. So why does it happen? Actually, it happens because partial specializations or like sphenae on special member functions are forbidden. So you cannot say, hey, if I don't know, the type is trivially copyable, define this copy assignment operator as 1, or like if it is not trivially copyable, like just like write your own copy with a branch. And this results in that optional has around 1,400 lines of code. Which is pretty big for the type that seems to be like, that looks like a pair of the type and of a Boolean variable if like the type presents. Unfortunately, this was a problem even in like real life. Actually, after optional was standardized and variant, then not at the very last moment, but pretty like in the last meetings, there was a proposal to propagate copy move triviality. Unfortunately, this like as you've seen, this comes with the complex design of optional, and actually there was on like somewhere on Stack Overflow a complaint that standard optional int is more expensive than pair of int bool. This was because this proposal was not implemented at the time in libstdcxx, and it was eventually fixed. So people complain about that it is not as performant as they expect it to be, and it is like eventually fixed, but at what cost? Another evil side of triviality are the types as standard pair and standard tuple. As for example, I present you a benchmark. We have a struct my pair. It contains 2 integers, A and B, and I just generate like a vector of 100,000 elements with this pair and a standard pair, and I just see and I just measure what's like the time to copy one object or another object. Fortunately, it turns out that my pair is 25% faster than the standard pair, and Why? Actually, the answer, again, isn't triviality. Unfortunately, standard pair has a user-defined assignment operator, and actually, that's not that hard. What's happened here? Let's see. We have basically a conditional type trait here. If the type is copy assignable, and the type is and the first type is copy assignable, the second type copy assignable, then use pair, and otherwise use so-called like underscore not a type, so which basically an empty struct in implementation for non-copy assignable, like one of the types, and it defines a first is equal to underscore p dot first, second is equal to underscore p dot second. So why is that different from writing equal to default? Unfortunately, this is different because it supports the reference assignment. So in pair and in tuple, you may have references as the template parameters, and you can assign easily from like references of standard pair, standard tuple. The same happens with tuple. For example, standard tie. In the previous talk, it was discussed. The previous talk on structure bindings in this const west room was discussed. And standard tie also works the same way. Like this is the implementation. Standard tie basically has as the arguments like the references, and basically you can write standard tie is equal to something. So, but and why, like when you write is equal to default, for example, copy assignment operator is equal to default, why doesn't it generate for references? Because it's forbidden in the standard. Default copy assignment operator is defined as deleted if T has a non-static member of a reference type. Why? Because it's not intuitive when you have, it's not obvious if you have a reference in your class. What should we do when we just assign one object to another object? Should we assign just the reference, like the pointer, or the class itself? So it was decided that it is not obvious what to do with the reference types, and eventually they just the classes don't generate the copy constructor, the copy assignment operator. So is equal to default won't work. That's why you need to define it on your own. Of course, like standard, as I've shown you, standard pair is not what you expect to be. Is not just like T first, U second. But there are some good news, of course, on this. For example, Clang tries to optimize, tries to combine the types like in registers. For example, here you can see if you have a pair of integer and integer, it tries to combine it in one like 64-bit register. At least we have something, despite the fact that standard pair is not performant as we expect it to be. But for tuple, tuple is a more complex type, and compiler just gives up and does like two moves. Unfortunately, tuple is not. For tuple, I haven't found any good reasons to be performant. Why can't we change? That's one of the biggest questions. So people just complain. We need to understand why can't we change the things. Partially because it's an ABI break. So what's an ABI? Like briefly. So translation unit, basically ABI is a translation unit interaction. So if you have a function that is mangled into some name, you need other translation units to understand this mangled name. So you need to somehow call this function in the binary. And what ABI break what they cannot do, they cannot change the name of, we cannot change the name of the function. We cannot, for example, change the number of bytes of the class because, well, like in one translation unit, for example, we prepare some class, and the other translation unit doesn't understand this like number of bytes. We cannot change the alignment. We cannot change like we must comply with the register with the calling conventions. So there are lots of stuff why we can't change. And for pair, why can't we change? Let's see, like we have two examples. First example, like two integers. Second example, two integers, but with default, here with user defined. And we have like two functions that copy like example 1 and example 2. Why can't we change? If we compile it, for example, with zero optimizations and see all the definitions in the Mongo name, we'll see that only one operator was defined. And actually, this is true for the type, true for the C++, if true for sys5 ABI. If you have a trivial structure, a trivial class, then all default operators like don't generate assignment operators, constructors, etc. So in that case, example, if we have somewhere like the call to the assignment operator, to example 2, if we change it to default, it will not link. Actually, the binary will not understand that there like such function even exists. On the other hand, there is a not very big ABI break because almost all structs and like almost all trivials, like the copy assignment, like these user-defined operators on copy assignment are inlined. So it might be not a very huge ABI break, but without optimizations, for example, even in modern compilers, you will see that this is definitely it. How to improve these things in the future, actually, regardless of like API. As I've noticed that you have, as I've mentioned, there are like optional is very complex type, and if because you cannot do any conditional any conditions partial specializations on these special member functions. There is a proposal, and I'm not sure if it was accepted or not. Like, or is it like by default will be with the concepts? But with this proposal, you can write, for example, in Clang, I was managed to write some sort of like conditional member functions, and the optional implementation went down to 390 lines of code. So it's like 3 times lower. So trick number 2, use equal to default in your code always when possible. So this, I put a lot of effort in explaining you why triviality is important. I believe I'm rather convincing. Of course, not all types may be in production code. Maybe like 90% of the types are not trivial. Yet, from my experience, the most like trivial types are the high-performance thing. They are just the low-level thing that you need to operate with. Now let's talk a little bit about debatable things like standard string. Standard string is a like sequence of characters with some properties. Lots of compilers, actually, that's encouraged by the standard. They use like smaller short string optimization. We are like in standard string, we must store like basically 3 things: a pointer to the start, the size, and the capacity. And small string optimization, like briefly, it just reuses these bytes when the string is small. So we don't need to store, we don't need to allocate, for example, like 6 bytes. We can store it like we can store the size in 1 byte, the capacity in another byte, and 6 bytes just like adjacent to it. So we might only need like you to use 8 bytes, and we should not allocate memory. I quite failed like looking when it was invented. Likely it was invented in like 2000, 2001. I'm not sure, but this is like pretty already like 20 years. This idea like holds like in a year for 20 years. And for example, standard string has some different, like small string optimization optimizes different number of bytes. For example, in libc++, it optimizes 22 bytes. In libstdcxx, it optimizes 15 bytes for a reason. Like to actually basically generate less code because it stores like size and like in another register. So we decided to use fewer bytes. For example, Microsoft STL uses 15 bytes. Facebook string is 23 bytes. Here is the link. When the slides will be shared, you can look what they have done to like win the last byte. And for example, where I worked at Yandex, there are like 0 bytes. It's fully copy and write. Yeah, so lots of modern implementations like try to use small string optimization. Yeah, this is basically how small like string is used. So you have capacity, size, and data. You'll just have one bit in the capacity, for example, like that defines if the string is small or not small. Then if it's big, then we set it to 1, and the data points just to the actual string. But if it's a small string, we just set the least significant bit to 2. In this first byte, we store like the size, and then we store like basically the data with \0 in the end. Standard string uses the technique of small object optimization, and not only this type uses it. Basically, standard function also uses the same technique. For example, as I remember correctly, in libc++, it uses like 48 bytes or 24 or 48 bytes. I don't remember exactly. Of like storing small functions that don't require lots of state to use. And this trick is very useful for highly accessed data. For example, we made some experiments at Yandex with replacing like string fully copy and write with this small string optimizations, despite the fact that there is like a complete API break, whatever. It showed us 2-3% of gain. So it's really helpful. Fortunately, with small string optimization, there is a cost of understanding what each operation basically has a branch, whether the string is small or whether the string is big. So this leads us to another good fact. For example, if you pass standard string by reference, you will pay the cost of understanding if the string is small or not small. So instead of it, use fancy C++ standard string view feature. It basically stores standard string view stores the pointer and the size. It stores it like in 2 registers. There are no interactions. It's a very cheap copy, always pass by value, so you don't even need to think how to pass standard string view. So, for example, with standard string view, as I've already mentioned, you need for each operation with the standard string, if it passed by reference, you need to pay a branch. For example, in libc++, to understand whether the string is big or small. But when you have a string view, you just don't pay anything. And of course, when you cast from standard string to standard string view, you need to pay the construction time of standard string view. But if you do a cascading pass by reference or cascading pass by this standard string view pass by reference, you might be able to benefit from passing just string view. A standard function also has some consequences with that. For example, if I've seen this code a lot, like people blindly pass the has the capture, the reference as the default capture. And unfortunately, if you reference by default, you need to have all the references in this. You need to get into the function all the references in the scope. So the small object optimization might die, or the compiler should understand more clearly that what you want to do, that you don't use some variables, for example. This leads to trick number 3 that I found quite useful, that try to use standard string view and standard span almost everywhere when you don't need the ownership of the continuous container. Standard span is basically a C++20 feature that's almost like standard string view, but for any continuous containers. They are cheap to copy. They are trivial. So all trivial types are good. And this also leads us to trick number 4. Always remember about small object optimizations. So this really helps to understand what's going on underneath your code. For example, don't capture blindly by reference in Lambda when you assign to standard function, or don't pass cascadely like the const standard string view reference. This leads to some consequences, some performance penalties, etc. Also, standard string view has some other problems. For example, if you have a vector, I haven't written the code, but assume it was filled somewhere in the middle with something, and you want to combine it like in one standard string, and the standard does not provide like some standard functions for basically doing it. That's why people always, not always, but I've seen this enough, they write that we just concatenate string part by part from the string. Unfortunately, this results in linear time of allocations. This can be extremely like resource wasted, and you can do better. You can basically resize the result with one number, basically the sum of the size of all parts, and then just copy all the data in this part. So standard string view not also a tricky type, but also like some operations with it. And as I know, all the libraries that I provided, they have something like that, like EASTL string join, fully join. They try to sum all the sizes, does one like sum, yes, they sum all the sizes, do one allocation. And a weird trick that I would like to share, that they try to use some non-standard extensions. Basically, libc C++ and libc provide the function called resize default init. There is a proposal of accepting this into the standard, but not yet, which basically resizes the string but does not default, but does not like zero the bytes that were resized. So you have like just raw memory allocation. And this leads us to trick number 5, which I've seen a lot, and even of C++20, write your own string operations library, at least something. Try to write standards like string join, try to write, if you have paths, like some splitters, like etc. Or use the existing external ones that, like for example, EASTL library is a good one. Now let's talk about unordered containers. I've seen in the chat there was a question about unordered containers. Unordered containers are tricky. There are 2 types from the computer science course of like usual hash tables. It's like open addressed and closed addressed, and unordered types are like closed addressed that use buckets for hashing. And turned out that it has some properties that are not actually used. For example, pointer stability. If you erase something from the unordered container, or all other iterators to the objects remain valid. Unfortunately, that's like, or fortunately, I don't know, that's not always people need. Unordered containers are also not the best one, because C++17 doesn't even support heterogeneous lookups. That means that if you have an ordered set of strings, you cannot look up by a string view. You have to pass like standard string in order to look up in this table. And many other libraries, for example, do. Many other libraries, like for example, EASTL flat hash set, does support heterogeneous lookups. And it was shown actually by our benchmarks at Google that unordered types can be outperformed by a factor of 10 or even 20. Here is the link to our benchmarks, like Google, GitHub, Google/hashtable benchmarks. It is shown like how different types of containers perform. And this leads us to trick number 6, which I've seen in many places. in almost any decent C++ code base that if you have enough hash tables, so hash table usages, and likely you will have hash table usages. Unfortunately, you need for now write your own one or use even the external ones if you want like the real performance of the hash table containers. Yet the type is debatable, maybe is borderline between debatable and bad type, and some libraries don't benefit from, I don't know, flat hash containers. Some do benefit. And at Google, we spend a lot of time, and is spending right now lots of time how to optimize, how to migrate to all unordered containers to flat hash map containers. And there is a good talk from Matthew. I don't remember the surname, but CppOnSea. There was a talk from Google about hash tables and how they are used at Google. Algorithms are pretty good, I could say. So algorithms, despite the classes, they don't have ABI problems. They're constantly optimized. They are doing better and better job. For example, compilers produce better SIMD code. And there are only several that are debatable. For example, people still argue about which sort is better, which element is better, but I strongly advise you to still use them because, in general case, they might not in your particular case they might not be the best, but in general case they are really a good default. Let's see how, for example, standard rotate works. For example, standard rotate has two algorithms, and it's GCD rotate and forward rotate. GCD rotate basically splits it's called also juggling algorithm. It splits your range into GCD and K elements and just rotates them around. But it requires random access. And forward rotate, basically, you have 2 pointers and you just swap the elements until you have a rotate. The detail of the forward rotate is a bit complex, but still. In the first one, you need only n plus greatest common divisor of any k that are swapped. In the latter case, you need to swap between 3n times, 3.5 times n times, and 3n times. But it can be done with forward iterators. And in libc++, we use in libc++ the memory, the iterator tagging is used. And if it sees it's trivially move assignable, then GCD, otherwise forward. So it also tries to dispatch the implementation on whether what's the iterator, what's the type of the iterator. And this is the forward iterator forward iterator tag. So just rotate forward. Copy basically is doing pretty much the same. If the type is trivially copy assignable, it tries to use a standard memmove. Memcopy, we cannot use memcopy because we're not sure that these 2 pointers do not overlap. I'm not sure, but I believe this is actually a bug because you can use only on memmove functions, only mem functions on trivially copyable types, but trivially copy assignable types might not be enough by the standard, but I'm not sure at this point. This is just a fun fact. For example, other good example of how algorithms are optimized in Microsoft Standard Library, there is a function reverse function is actually SIMD optimized. They try to hand vectorize the things with very complex SIMD, some permutations, some stores, etc. So this is just an example of how algorithms are optimized, and they are evolving always in the libraries without any ABI or API breakages. Another good algorithm, I said that it is debatable. Yeah, standard sort. It must have n log n comparisons. people debate about what's the best algorithm. For example, one decent algorithm, it's like PDQ sort, which turned out to be like pretty good default. Intersort, count sorts, all the sortings. Like I've read like a week ago that there is like machine learning sorting that tries to optimize quicksort for the specific data. And unfortunately, sometimes it has surprises. For example, libc++ has quadratic sort. libc++ sort is basically a QSort with some tricks. Here is a link to the bug where it was first known, and the example is pretty simple. So if I don't want to go into detail like why it works like the quadratic time, but basically there is an algorithm. Here is the link that tries to kill all QSorts that do some constant comparisons to understand the medians or like the three medians, etc. So unfortunately, sometimes standard library has surprises, and for n is equal to 1000, libc++ uses n squared over 4 comparisons, and libstdcxx only like 30,000 comparisons, which is basically like 3 times more than n log n. But on the other hand, it has some advantages, for example, for some non-very random, not very specific data. For example, if you have some good patterns, standard sort and libc++ tries to find, tries to understand it and optimize it for that case. So yes, standard sort, as it turned out to be, had some and has some surprises, but on the other hand, it's very good thing for the real usage data. Another algorithm with a bit surprise, it's called standard min-max element. Standard min-max element does not call min element and max element and then just returns the value. It uses 3 over 2n comparisons. Basically, like first it compares the consequent pairs. Then all that lost the comparison, for example, all that are lower goes in one place, all that are bigger in the other place, and then they try to find from the first half the minimal, from the the biggest, from the second half the maximum element, and you can prove that you cannot do like fewer comparisons, but unfortunately, this requires some dispatching of the logic, and it can be worse for trivial types. For example, in this benchmark, I have min-max element calling the min-max element and the minimal element and the max element on the vector of integers. And as you can see, the standard min-max element is worse by 15-20% than hand min-max element. So has some surprises, but it's like and 3n over 2 comparisons is basically a standard. It's written in the standard. You must have this number of comparisons. This is good for example, for more complex times. For vector of strings, you don't want if you save, I don't know, half of all this comparison. If you save 25% of all the comparisons, that's even better. So it has some cost for trivial types, but it's actually better for most of the other types. So this leads to trick number 7. I combined it is that try to use standard algorithms. They are almost always good and they're constantly improved. So they don't have problems that they cannot evolve over time. Atomic, I will be brief about it. So Atomic has a really good design from my perspective. It supports memory models where you can mathematically understand what happened before, it's called happens before memory model. Atomics are supported on most of the architectures, like cache coherence, developed pretty good for the past several decades. So atomics are also supported already in CUDA, and volatile is deprecated, and try to avoid using volatile. So atomics support most of the memory models that are used in modern CPUs. I advise you to watch the Jeff Bastian talk about deprecating volatile. It has lots of fun. Why people were using volatile, what it actually means, and why you should not use it, and why in C++20 volatile is deprecated in several cases. So use atomics. They are sane, and basically I haven't seen that anybody forbids the usage of atomic library. Standard regex. Let's talk about a little bit about pain. Standard regex needs to support lots of grammars. It's called BRE, ERE, grep, sed, AFC, whatever. And all these grammars become the part of ABI. Unfortunately, it is very hard to change, to evolve the standard regex and to optimize things. For example, standard regex is 20, 30 times slower than any other regex, any other decent regex. And this because it needs to support lots of different grammars and to support different kinds of DFAs. And standard regex also doesn't work well. For example, in libstdcxx, for example, it crashes when in libstdcxx it crashes when matching long lines. This issue was not fixed for 2 years. Somebody has found that standard regex corrupts the memory. It hasn't been fixed for 6 years, and some resource exhaustion, so it blew up in some places. So this issue also was not fixed for 6 years. Fortunately, standard regex is kind of a doomed thing, and I believe everybody should agree that no one should use standard regex. There is a question in the chat: what should people use in standard regex? I suggest several things. Try out RE2. It's the library from Google. Try out Hyperscan. It's a very optimized x86 regex engine. PCRE, CTRE from HANA Dusicor. That is compile time regular expressions. Boost regex is also much better than standard regex. Try to use it if you don't have other options. And yeah, basically that's it. They are 30 times better, 50 times better than standard regex. So what's happening in the real world? Unfortunately, C++ is not only about readability. It's a balance, I could say. So people should be able to read your code. Unfortunately, the real speed, I don't know, all the compilers are not gods. They cannot provide you the best algorithm, even in theory. So there is always a balance between speed and readability. I don't think that it's worth optimizing last percent if it costs lots of readability. For example, if you need to educate some people that, hey, this function does that or does that, maybe that's for 100 people and you've saved, 1%, that costs maybe, 1 server a year. That's not worth doing it. So always try to find the balance and don't overcomplicate your programs when you're writing code. Also, when you write your own your own fast things, I could say, there is always a cost of debugging, occasional bugs, etc. So, and they happen. Unfortunately, they even happen in the standard libraries. Unfortunately, everybody writes bugs, and you need to understand there is a probability that you will write bug. Maybe it's not worth it. So let's talk a bit about practical things. There is a lot of debate what's better, libc++, libstdcxx. ClickHouse is a Yandex database. And once we decided to update the standard library from libc.c++ to libc++. And it turned out to be that the overall performance is about 2%. And some pretty formats were improved even about by 40%. So it was a good experience of migrating, and it was very nice, I could could say. So it was a very good experience to try out two different things. And also, don't forget to update your standard. That's also true that standard evolves and it provides you better performance features. For example, in the picture on the right, you can see that there are some basically there was a patch of like enabling char-at in ClickHouse. Char-at basically is a type that does not have aliasing rules with other pointers, unlike char star. So and ClickHouse had pretty many places where they can use char-at and not like just pointer to characters. So, and it was a 2% win. So, for example, on the right, you can see that there was some reduction in some code by like several instructions. There were like lots of places where it was used. Also, from C++14 to C++17, it was a very interesting experience. I don't understand like particularly why it happened, but no except like in C++17, no except is a part of a type system. Maybe it's saved a bit like of the exception propagating. I don't know exactly. Maybe copy elision took place. That's the like less data, less code was generated. But on one service, we like clearly saw the 99% like quantile win, and we were very happy about it. And we are sure that no other changes were happening except the switch to new standard. So trick number 10, more general one, write benchmarks for your code, try different things, find your own best combination, but don't complicate too much. And talking about ABI breakages, there might be a solution in the future of C++. For example, in Prague, the C++ committee decided that they can consider ABI breakage proposals only for huge performance wins, and we should be able not to break much. And most likely, the most important part, we should be loud about the decision, whether we broke something or whether we are going to be stable. And the last trick, always remember that C++ is more than just performance. That's it, and I am going to the question part. So why is an order containers? I've already answered it. What do people use instead of standard regex? I already answered it. RE2, hyperscan, CTRE, etc. Why is tuple banned in many places? How exactly is it a bad type? It is not banned in many places. In the slide, I showed you that it was only the last two were banned in many places, but unfortunately, standard tuple is not good for example, for serialization or deserialization. So last two are banned in many places. So not standard pair, standard tuple. It's a thing that people don't actually know the performance penalties. You named standard vary as a good data structure, but standard visit is considered to be slower than using a switch statement. How do you recommend using variants? Yes, I know that standard visit use some RAII in standard visit. I mean, I was talking about standard variant that it propagates the copy and triviality when the underlying types are trivial. So I haven't considered like the standard visit yet. Yet I believe like standard variant. I believe there are a few cases where standard variant might be performance critical. So use your own decision. If it is really performance critical, try to use switch statement. If it's not, try to use the readability thing as standard visit. Which benchmarks tool do we see use here? It's called CppBench. For example, from Godbolt, you can there is a direct link to it. What are the errors on the timing measurements? In the benchmarks I provided, there is around like 2-3% error, but on the other hand, like overall, it is like I believe it is still around 2-3%, like in the real world. So if you if your benchmarks is like decent enough, it tries to use some statistical testing. What exactly defines the scenario for not using standard unordered? Does this depend on the size of the object stored, number of items in the container, as well as the frequency of use? It's a difficult question. I could say that I believe almost always flat, as it was shown by our hash table benchmarks at Google, we believe that there is no case then when standard unordered map or set can be used. We saw several cases when it was slower, but it was mostly because of because of hashing was not very good, or when we changed to other hashing, it was worse. It became better. So I believe you should. There are like hash tables that are faster than standard unordered almost always. Matt Godbolt, great talk. Thank you so much. Thank you. Why is tuple banned in many places? I already answered this. Is it the way that the standards defines the unordered containers that makes it impossible to implement them efficiently, or are they just the implementations just bad? It's basically the ABI problem. You cannot change the underlying objects, and if you have like bucketed hash table and a flat hash table, you cannot switch from one to another, not replacing the underlying storage. That's why basically, if you wrote the implementation, you cannot change it. What's the magnitude of the contribution of using bad types on the performance of the whole program? It might be different. Overall, it can be up to even 50%. From my experience, it can lead to, like, as I've shown, like, for example, we tried performance stuff in ClickHouse, for example, changing one library to another library where some bad types were a bit better than the others. And we saw like 2% performance win, but it depends. For example, we replaced all handmade joins with our joins at Google, and it also showed like some good performance gain, benefit, etc. So I believe I answered all the questions. I'm a bit out of time. And I believe that's it. I believe we can stop the stream.